Before going before going more deep into the research area, I'm going to talk briefly first about the latest deep learning that we are using currently, deep learning models. So we all have seen some sort of machine learning or deep learning models so far, and we know that the basic building blocks that in all of our models that we're using in all of our algorithms is what we call it the neuron. The neuron that is basically computing the weighted sum of its input and pass it to the nonlinear function. So it's basically applying linear regression and pass it to a nonlinear function. And then if we want to build a neural network, we're stacking neurons to build up one layer, and then we're stacking multiple layers to build up a neural network. So neural networks takes a single input and provide a single output. Now, one of the very important questions to ask when we're using a neural network is that, what if we would perturb our input to the network? What's going to happen to the output? Or how can we figure out, or what the network is going to provide us information about this perturbation that's happening at the input? Or how can we judge if this single output that the neural network is providing is robust enough and trustable enough that we can use in real-world application? And since I'm going to be focusing more on imaging science application, we usually use convolution neural network, where again, the basic building blocks on convolution neural network is the convolution layers, where we are applying kernels that perform the convolution operation, which is also a linear operation, followed by a nonlinear function, and then we stack multiple layers to extract multiple levels of information from the input images, and then we pass the information or feature maps that we extracted to fully connected layers to perform either classification or regression problem. Again, the same question applies here. If our input image is perturbed by any sort of perturbation, what's going to happen to our output? How the output changes, and how the neural network is reflect to that perturbation at the input. So this is what we're going to be focusing here in our talk. So we all have seen neural network have been integrated in many different applications, from healthcare to self-driving vehicle, self-driving cars, for cybersecurity, and many other applications. And one of the very important question is that, how much can we trust the decision that is made by these networks? If the network is providing us with a specific decision, how can we depend on that decision if we're using the neural network in one of these important applications? So this is what made robustness is even more important when the idea of adversarial attack came into the literature, which is basically, what is adversarial attack or adversarial perturbation? So these are images from the first paper that came in with the adversarial attack in 2015, where people tried to come up with imperceptible type of noise that is added to the image. So the noise is imperceptible to the human eye, so the user cannot see if the images are perturbed, but the network and the network is making wrong decision, and on top of that wrong decision, the confidence on the probability output of the neural network is very high. So when the network is predicting the output, it's making a mistakes with a very high confidence that's not even telling us that there's something wrong, or there's some sort of perturbation to the input that we need to be aware of if we want to use the neural network. And this is another paper that's showing that this is going to be have a disastrous consequences if we're trying to use a neural network, for example, in self-driving car, where a stop sign can be predicted by something else, like a speed sign, and it's going to be misinterpreted by the car by something else, and not being noticed by the driver. So what you see here on the top, this is using the handwritten digit data set. This is a small experiment we did in the lab, where we try to inject adversarial noise, and we change the background of the image so we can actually see a little bit of the noise, so it's not completely imperceptible. And we look at the output of a convolution neural network for predicting that is trained on a clean data that never, so the network have never seen this type of perturbation before. So the output of the softmax, which is the output of a neural network, it's usually a vector with values between 0 and 1, and they all sum up to 1. So it's more like a probability vector where the maximum usually refer to the predicted class. So when we look at the output for the network, we see that it's predicting this image as digit 3. And here we were trying to target digit 3. So we wanted intentionally to fool the network to think of any image that this is an image of digit 3 from the handwritten digit data set. So the network predicting the image as digit 3 with 0.9976 versus the ground truth, which is the digit 1, and that we can clearly see that it's digit 1, it's getting 0.01. Sorry, 0.2. So the network made a mistake, and it's also not giving us any intuition that it's actually making a mistake because of the perturbation that's added to the image. So that's mainly like a motivation why that driving the main importance of why do we need to care about robustness when we are using neural network for solving any problems in our research. So what do we need in order to be able to trust the network? We need to quantify some sort of confidence or uncertainty at the output that will tell us if the prediction that is brought to us by the network is trustworthy, so we can depend on that decision, or if the uncertainty or the uncertainty of that decision is high, means we cannot really depend on that prediction much. So one way in order to emphasize uncertainty quantification in a neural network is through the Bayesian theory, where we assume that the parameters of our network are no more deterministic numbers, but distributions. And we want to propagate that distribution through the network. So the output will not only be a single output vector, but it's going to be a distribution, where from a distribution, we can extract a lot of information that will help us to know if we can trust the prediction by the network or not. So the Bayesian theory mainly say that we can assume that we inject some prior knowledge about the network parameters. We call it prior distribution. And after observing the data set, and mainly training data, when we train the network, we want to estimate the posterior distribution, which is mainly the probability of the parameters of the network, given that we've already observed the data. Now, this can be computed using Bayes rule. Now, one might ask, why do we need the posterior? Like, why do we need the probability over the parameters? We're not directly interested in that posterior. We're mainly interested in it because we're interested more on the prediction distribution, which is the distribution over our output that can be computed by integrating over the old network parameter using the posteriors. So we can't actually compute the prediction distribution, which is the distribution over our output for the network, unless we have the posterior. So the main goal for estimating the posterior distribution over the parameters for the neural network is to be able to have access to the prediction distribution and be able to extract a lot of information from that distribution, statistics like variance, for example, that can at least tell us if we can give us some information about the uncertainty on that prediction. Now, the problem is that one step back, applying Bayes rule directly, you see like we have this summation if we have a discrete distribution. And this is not really possible for a neural network. We have a large number of parameters, and not only this, we have multiple stages of nonlinearity, as we have mentioned at the very beginning. So we have a nonlinear function for every single neurons for every single layer that will not be able really to estimate the posterior distribution directly. So one way to address this problem is to approximate that distribution. So what we did, we used variational inference. So the main idea of variational inference is that, well, if we don't know the distribution, let's try to approximate it by some parametric distribution. So here we assume it's Gaussian, and we try to minimize the similarity or difference between the unknown distribution that we don't know, we'd like to approximate, and the parametric distribution that we assume. which here we mostly assume Gaussian distribution. So the similarity measure or the distance measure between the two distribution, we call it the Kullback liberal divergence, or as an abbreviation, just the KL divergence. So we basically want to choose a family of distribution, we mostly Gaussian, where the mean and variance for that Gaussian is unknown. And we want to minimize this difference between our unknown distribution and this family of parametric distribution by estimating the mean and variance for this unknown, for this parametric distribution that we assume. So if we write the formula for the KL divergence and just fix the equation, so we'll see that our objective function is going to be two terms, where we have the expected log likelihood term, which directly depends on our data. And the second term is the KL divergence between the variational or the parametric distribution that we assume and the prior distribution, which we also know, because we also impose an assumption about our prior distribution. So the second term is more of a regularization on the unknown parameters, omega, and the first term depends on the data. So what we want to optimize this objective function. Now, one of the advantage of applying variational inference is that we can turn the density estimation problem, which is trying to estimate a distribution, which is the posterior, into more an optimization problem where we can optimize this objective function. And we can use the advantage of back propagation when we are just like when we try a neural network. So we assume now we have a distribution over the parameters, and we would like to propagate that distribution over the network. We have a distribution over the output, and we have an objective function that can take the mean and variance for that distribution and optimize it. Now, there's still one problem that we need to handle, is that, well, our regular neural network is usually applied to deterministic numbers, like the matrix multiplication, convolution, or nonlinear activation. Those are applied to deterministic numbers. Now we have distribution, which we assume Gaussian with mean and variance, or covariance matrix, because it's a multivariate Gaussian. Now, how can we apply the same mathematical operation? Well, we need to redefine this mathematical operation in order to be able to apply to distribution or to random variable with the probability distribution. So what we did, since we say like we're going to be propagating the posterior distribution over the network, and since we assume it's Gaussian, and Gaussian is fully representative by its mean and covariance, so let's propagate only the mean and covariance for that distribution, because the mean is going to lead us to the prediction at the output, similar to deterministic, but the covariance matrix is going to provide us more with uncertainty information. So we're going to propagate only the mean and covariance, and we need to redefine all mathematical operations. So for the linear operation, like matrix multiplication and convolution, or inner product between two random variables, this can be done analytically, which means we define the analytical solution. The problem that comes is that for the nonlinear activation function, this is not an easy problem. We need to find a way to propagate the distribution, or the mean and covariance for that distribution, through a nonlinear functions. So that's why we define 3 different ways in order to propagate the distribution through the nonlinear function. Since like this is a non-feasible problem mathematically, we need to figure out a way to do it. So we define 3 different methods that I'm going to go through. So one of them, most of them are inspired more from signal processing, like Kalman filter, and more of its variation. So the first one is to so the first method is simply to linearize that function. So I'm going to go through each one separately. So the first method is to assume linearizing that function, which means we're going to apply first order Taylor series approximation. We're going to write the function using Taylor series and approximate that function up to the first order approximation. So, and then we compute the mean and covariance, which is the expected value and the covariance matrix of the both sides of the Taylor series, all the way up to the first order derivative. So this is the first, and I know like it's accumulated with error because we're approximating only up to the first order, but we wanted to see how the model is going to work for this simple approximation first. Well, since we say like the first order approximation might accumulate with a large error, so let's try a different way of approximating. So we tried uncentered transformation, which is proved mathematically that is accurate up to the second order for Gaussian distribution. And the main idea for the uncentered transformation is that we're going to be generating specific number of samples from the input distribution before the nonlinear function. And we call these samples sigma points that are, there is a specific way of designing those points using the mean and the square root of the covariance matrix. And once I define those sigma points, we pass them through the nonlinear function, and then we compute their sample mean and sample covariance matrix. So first we generate those sigma points, we pass them through nonlinear function, and then we compute their sample mean and sample covariance matrix at the output. And that's going to be applied to every layer when we face a nonlinear function in the neural network. The third way is by applying ensemble method, where we're also going to be generating points, but now we're going to be generating random points, which means we're not, one thing I didn't mention about uncentered transformation. So here the number of sigma points is restricted to the dimension of the input. So whatever the dimension of our input feature map is going to be 2 times this dimension. So we're not generating large or small number, we're restricted. So this is by definition of the uncentered transformation. We're restricted to 2D, which is 2 times the dimension of that input vector. For the ensemble, we generate random number of points, just like Monte Carlo samples. And here we're generating random samples from the input distribution. We can, the larger, the better. So we can generate large number of samples. We pass them, we compute also the sample mean and sample covariance. Now, after applying this to all layers of the neural network, at the output, we get the mean and covariance matrix, where the mean is going to give us a prediction for whatever the input, either if it's classification or regression or segmentation. This is all applied. We're going to see multiple applications now. And the covariance matrix, where mainly the diagonal, are going to provide us with uncertainty measurements about the prediction. We're more interested on the diagonal. We also did some experiments of the off-diagonal entries for the matrix, but we're mainly interested in the diagonal because we want to estimate the uncertainty for the prediction. So we started with a simple experiment using the handwritten digit data set, where we trained the network on this data, and we want to test it while injecting noise to the test samples and gradually increasing the level of noise. And at every level, we compute the output, the average variance for all test samples. So the number of test samples is 10,000 samples. So we inject like the same level of noise for all test samples, and we compute the signal to noise ratio and the average variance. And then we do that for multiple levels. So we read these graphs from right to left, where signal to noise ratio is decreases, means the noise level is increases. Now we notice when we do this, like if we look at the blue curve, we see like when we have adversarial noise specifically, the variance, which is the top, I don't know if you can see my cursor, the top graph, the variance increases when we have more noise, when we have a small SNR, which means we have larger level of noise, higher level of noise. And that's for adversarial noise, even more than Gaussian or random noise, which is the red curve. Now, the highlighted area is the error bar around the variance that we computed for each experiment. For the subgraph on the bottom row, we plotted the accuracy versus SNR, because we wanted to see at the same level, when the variance increases, what was the level of accuracy for the neural network. So we see that when at the beginning, when the noise, like when the SNR is high, the noise is very low. Well, the model was performing almost the same. It's very close to 99%. This is very close to accuracy without noise. But when the noise starts getting much higher, the accuracy for the model start to decrease. But at the same time, the model have a very large variance that's telling us that Well, this prediction, although accuracy is low, but the variance is very high. Now, we did some comparison here where we wanted also to check how our model is doing versus deterministic network. And we see that even that the accuracy drop at the very high level of, this is adversarial noise, like 66% for unscented model and 51. Well, the deterministic network, the regular network, performed 14%, which is the level of random guess, because we have 10 classes for digits from 0 to 9. So the network without uncertainty quantification performed the level of random guess, versus the Bayesian model with uncertainty quantification. It's still able to realize the digits, and even when the accuracy drops at some point, the variance for that model becomes very high, significantly higher. We run similar experiment, but now for more complicated images, like these are colored images of real objects that are compressed between to 32 by 32. This is called Cipher 10 dataset. Also have 10 different objects, and we run similar experiments by training the model on clean data and tested under noisy data by increasing gradually the level of noise. And we noticed that the variance for the model also increases significantly when we have a very large variance, when we have a very large level of noise injected at the test set. So here we wanted also to check if we can use this variance more for anomaly detection, which means if we have an anomalous samples that's not very similar to our training data, can the model figure out that there is an anomalous samples and give us some information about this? So we run an experiment where we try to look at, so here we were also using MNIST data set, while we inject 3 different level of noise. So the first one is Gaussian noise. This is adversarial noise. It's called FGSM, which is fast gradient sign method. But this is non-targeted, which means applied to all classes. And this is targeted attack, which means we're targeting a specific class to fool the network. And we plotted also the variance, but now we want to differentiate the average variance for all test samples versus the variance for correctly classified samples and incorrectly classified. So we wanted to see when incorrectly classified or misclassified samples. So here where the model is actually making mistakes. So we wanted to see how the variance is different. And we noticed, this is the green curve. We noticed that even for the low level of noise, the variance for the misclassified sample that's presented by the green is always higher. So the model, which means whenever the model is making mistake, it's providing a very large variance as compared to the variance for the correctly classified sample. So it's not randomly increasing the noise for all samples. It's the model is having a large variance specifically when the instances are misclassified by the neural network. So this is a similar experiment, but for the Cipher 10 data set. So here we're designing 2 types of thresholding technique. We say, like, we want to set up a threshold on that variance in order to decide if the input sample is anomalous samples versus just a clean samples or like similar to the training data samples. So we designed 2 types of thresholding technique. One, we call it static threshold, where we basically compute the average variance over test samples when we have a clean samples, when we don't have any noise injected on the test samples. The other method is called statistical, because we run a statistical test. Let me go just one step further. We run a statistical test between samples at the low level of noise or without noise, and the variance for test samples at every level of noise. So we first compute that. So we have 10,000 samples. We have the variance for the clean samples first without injecting any noise. And then we have once we start injecting noise, we have the variance for those test samples under noisy condition. So we run a pairwise statistical, it's called Wilcoxon sign rank test, in order to see where is the variance is going to be statistically higher, with the p-value 0.01. So we're going to refer to that data, to that level of noise as here, after this level of noise, the sample is going to be anomalous samples, which means like it's going to be anomaly. There will be like either adversarial noise or any type of noise, or it's just anomalous samples that maybe like not very close to our training data set. And we try to apply this to detect anomalies. So what we did, we ran an experiment where we trained the model on MNIST dataset, which is the handwritten digit dataset, and we choose another dataset which is very close to it, but different types of classes. It's called fashion MNIST, which are objects of different clothes. It's different than the digit, but it has similar structure, same size of images, 28 by 28, and they are also like a grayscale. And similarly for Cipher10, we choose another data set to check anomalies, which are also colored images, similar structure, but different type of classes. So we trained the model on one data set, and we want to test it both on the same data set and on different data set, where the testing on different data set, it's basically to check for anomaly detection. If the model is going to detect that, well, these samples are not really similar to what the network is trained on. So we define the true positive and false positive rate, where true positive means the model is going to take any images from fashion images and pass the threshold. The variance is going to pass the threshold, which means the model is successfully detected that those images are anomalous, are not similar to our training data. While false positive, when the variance of the model is passing the threshold for the same samples from the same data set. It means like by mistake, the model is giving high variance for similar samples from the same data set. And then we plot true positive and false positive, and the number of samples is 10,000 samples. So we see like that the model, the false positive for the model is less than 500, while it was able to detect all of the anomalous samples more than close to 80%. So the model was able to detect most of the samples that are coming from a different data set and assign them as anomalous samples, not related. So this is very important because many times in many applications, we always have what we call it outliers or samples from the data that follow a different distribution. And what we want our model to notify us if the model is making mistakes, or even if there's an anomalous sample or someone trying to attack our system for some of the application, we wanted the model to notify the user by giving a very large variance. So most of the experiments that we talk about was more on imaging data where we have convolutional neural networks. So here we wanted to extend the work for sequential data, where we use long short-term memory. It's more like a recurrent neural network. It has a gate structure where the data set were for power consumption and prediction. And we run the similar experiments, except now here for we don't have accuracy. We usually use root mean square error for check the performance of the model. And we also plot the variance under different level of noise that are more suitable for sequential data. And we also notice a similar behavior. The variance, when there's a very large of noise, high level of noise, the variance of the model is increasing. And the star is referring to the statistical increase when we run the Boxon rank test, sign rank test. So here we wanted to, this is a project we wanted to apply the idea for simulated robot, where we're applying it to reinforcement learning, where we're using actor-critic model, where the basic idea here it's for solving simultaneous localization and mapping, where basically we're having a simulated robot that is navigating an environment and trying to map this environment. And what we wanted to do, we wanted to quantify uncertainty over the action of that robot in order to increase its robustness for mapping the environment. So this is the simulated structure for the actor-critic, where we have two neural networks, one for the actor and one for the critic, where the actor model is for providing an action after taking information from the environment. And the critic network is also taking the state from the environment and criticizing the action that is done by the actor model. And the loss function that is optimizing both network is called the temporal difference error, where Well, here it's not a supervised, it's more like a reinforcement learning problem that works more by the reward. Every time every time the robot is making wrong action, the 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 model is going to provide a negative reward to penalize it, and then it's going to keep going until the robot is going to be correctly mapping the entire environment. So here I just want to show you after training for multiple time multiple number of episodes, it was able to navigate the environment without hitting the wall. So this is the result for the actor critic model, where we usually look into not the accuracy, but the reward, because the higher the reward, the better the model. And we also injected noise to the environment. After training the model, we injected noise to the environment and viewed the SNR and the variance. So here we injected adversarial noise. So for the actor critic model, so the dash one is for Gaussian noise, the blue one is for adversarial noise, and we can see how it increases when we have larger variance. Now here, this is the reward, and the red one is for deterministic actor critic, same model but without uncertainty quantification, and the blue one, the blue curves showing the reward, the average reward for the Bayesian model with uncertainty quantification, and also both for Gaussian noise and adversarial attack. The dash one for Gaussian noise injected during testing, and the solid line is for adversarial attack. This is one of the application with my collaborator in the MR for the company, industrial company, it's called MRI Math, where we wanted to do brain tumor segmentation, where we have 5 regions for the tumor. The edema tumor core, the blue one, the enhancing tumor, which is the red, and then necrosis, the dead cells in the middle, which is shown in blue. And we will also build up, now here we build up more like, it's a convolutional neural network, but for the encoder-decoder structure to be able to feed an input image and give us the segmented map. So basically, we're doing a classification per pixel at the output. And you also run an experiment where we inject, but here we inject like a very small amount of adversarial noise, because we just wanted to check how the model is performing. So this is the ground truth. This is the this is the model without noise, extended model. This is with adversarial noise. This is the unscented model and with noise, and this is the deterministic network. And what we plot here is the uncertainty map, which is the uncertainty, the variance for each pixel. And we can see that the variance is mostly over the boundary of the tumor. Now, this is very informative for neurologists to be able to check this uncertainty map before using the segmentation map for any treatment that might work. So the table here is just showing the performance, and we usually, for medical imaging, we usually use the DICE similarity coefficients or DICE score, where the higher the better, and we wanted to check the performance of the model first without noise, the first column, and then after adding serial noise and Gaussian noise. And we can see even without noise, the model performs at 85% versus 78% for a neural network without uncertainty quantification. So I just wanted to mention like multiple application to the neural network and emphasize again on the importance of robustness whenever we want to integrate neural network in any of these applications. We wanted to make sure that the model that we're defining and building to solve a specific problem is trustable and can be deployed in the real world. Okay. Thank you very much, and thank you for your attention. Any questions? Questions?